Williamson synthesis is a two-step reaction and is used to make a simple ether. Ether is an organic compound with an oxygen functional group. The oxygen is connected to two carbon chains. The carbons can be cycles and they can be benzene, so the hybridization of these R's vary between sp, sp2, and sp3. When you look at ether, you have two weak bonds. And the weak bonds are these two sigma bonds in there. So these weak bonds, we can simply break them. So these weak bonds can be broken. So I can break simply the ether from this side, or I can break the ether from this side. Either way, there are conditions for Williamson synthesis. And the reaction normally starts with an alcohol. So you would need an alcohol. The hybridization of this R can be an sp, can be an sp2, and can be an sp3. So there is no limit for the hybridization of this R. And the alcohol is going to go ahead and lose a hydrogen by a simple acid-base reaction. So this is going to be step number one in the Williamson synthesis. You start with an alcohol and you simply use a simple base. Now, your base has to be a strong base, and the best base to use for these types of reactions is the hydride. So we use sodium hydride, and that base, or any strong base that is capable of taking this weak acid. So you would need a strong base. Okay, so we're going to use this base in there, and the base is going to go and take this acidic hydrogen and form what we call an alkoxide or a good nucleophile. Now pay attention. This guy is a nucleophile and it's a base at the same time. So I'm forming the sodium alkoxide plus, of course, my hydrogen gas in there. So this is going to act as two roles. So it's going to act as a nucleophile or as a base. The role of the alkoxide is simply determined by the next step. So it's very important in the next step. If you want the next step to go by substitution, you have to use a primary or a secondary alkyl halide. Primary is the best. Methyl halide or primary are the best to go by substitution. And if you wanted to go by elimination, then you're gonna start with a tertiary alkyl halide. Since we're making ether, we don't want elimination. So in the second step, what we are looking for is the alkyl halide. So this is step number 2. We're gonna choose an alkyl halide, and that alkyl halide has to be a methyl halide or a primary alkyl halide. Those are gonna work best. We're going to use that strong nucleophile now because we're working with a methyl and the primary, so we won't have any elimination in there. And again, this is not bulky, so no elimination is going to proceed with the primary alkyl halide. Here you go. So you are going to use this nucleophile now there. So it's going to here act as a nucleophile. It's going to act as a strong nucleophile. And again, why it's strong? Because it's a negative charge. So it's going to act as a strong nucleophile. The mechanism is going to go by an SN2 reaction. And this nucleophile is going to attack the sp3 hybrid carbon. So that is an sp3 hybrid carbon. And the halogen is going to leave. And we're going to end up getting our ether in this case. So you notice that the ether has two sides. One side that is connected to the oxygen, that should be from the alcohol. And the other side should be from the alkyl halide. So if I want to choose the side of the ether from the alkyl halide, I want my R to be the less hindered side. So let's say, for example, if I want to go ahead and synthesize this ether. The first thing that I would need to look at are the R groups that are connected to the oxygen. And I want to pick the less substituted side to be my alkyl halide and the most substituted side to be my alcohol. So here, these are my two R groups. I have an isopropyl group here. So I know that this one over here is going to be, this carbon is going to be a secondary. Why it's a secondary? Because it's connected to two carbons. So that side is going to be a secondary side, and the other side of the ether, this is my carbon over there. So this is the other side. So let's highlight that other side. That other side is connected simply to one carbon. So this is going to be my primary side. You choose the less substituted side, and that is going to be your alkyl halide. So your bond breaking is going to be from the less substituted side. So you're going to break this bond. You're not going to break this bond. So you're going to break this bond here. And when you break, you're going to end up having two portions of the molecule. The first one, you're going to stick a halogen to it. So for the first one, this is an ethyl group. So I have an ethyl, and I'm going to just stick a halogen. The halogen can be chlorine or bromine. Okay, chlorine, bromine, or iodine. We do prefer to stick to chlorine or bromine. So I'm just going to make it a bromine over there, or a chlorine. It doesn't matter. And then the other side with the oxygen is going to be the one with the alcohol. So these are the two components that when I react them together in presence of what? In presence of a base. So I need a base in there. And the base is the hydride. So when I have these two, I react them together in presence of a hydride, then the hydride is going to come in the first step, take this hydrogen, make the alkoxide, and then that alkoxide is going to attack the carbon and the bromine is going to leave. So let's go ahead and write down the reaction mechanism in there. So step number one, always in step number one, I need to make my nucleophile, and the nucleophile is made from the alcohol. So you choose your alcohol in there and you react this with a base. Again, the base has to be strong enough in order to pull out this weak acidic hydrogen, and the hydride does the job. So the sodium hydride is going to come, is going to take the hydrogen, form the alkoxide, and I'm going to make my alkoxide in this case. Here you go. That is an Na plus my hydrogen gas. In this second step, we are going to use our alkyl halide, and we're going to react this with the alkoxide. And we are going to make our ether. So please pay attention that our alkyl halide has to be, since this one is an SN2 reaction, it has to be either a methyl halide or a primary alkyl halide to push the reaction towards 100% substitution, and you only get your substitution product. If you start with a secondary alkyl halide, then you're going to get both. You're going to get the SN2 and you're going to get the E2, which is a contamination to the product. So you don't want this. And if you start with a tertiary alkyl halide, you are going to push the reaction towards E2 elimination. You will not get any substitution product. So for lab 11, we are making benzyl methyl ether. And these are the starting materials that we are going to use. So let's go ahead and draw the ether that we are going to synthesize. So we're making a benzyl. So we know what a benzyl group is. It's simply a benzene. And that benzene is connected to a carbon. This carbon is called a benzylic carbon. And on the other side, I do have a methyl, and this is an ether. When you name the ether, you name both sides, both R sides, and you stick the word ether at the end. So if I want to name this, then it's going to be an ethyl. You arrange in alphabetical order. E comes before the I in the isopropyl. So this one's going to be an ethyl isopropyl ether. So this is the benzyl methyl ether. Now, if you want to prepare it, you can notice over here that both are groups that are connected to the oxygen. One is simply a primary. If we stick a halogen on this carbon, that's going to be a primary alkyl halide. If we stick a halogen on this carbon, it's going to be a methyl halide. And both can work. So both sides can work. This means that I can break either this bond or this bond. So I have two options in there. So if I go ahead and break this bond over here, then I am going to have my alkyl halide to be the benzyl chloride. So that is going to be the benzyl chloride, and the alcohol to be the methanol. Okay, so this is going to be one route. The benzyl chloride is a primary alkyl halide, so that is going to work with an SN2 reaction. Or we can go ahead and break the bond between the CH3 and the oxygen and have all the side to be our alcohol. So now our alcohol is the benzyl alcohol. This is going to be the benzyl alcohol plus the CH3 over here is going to be our alkyl halide. So it's going to be a methyl halide. The X can be either a chlorine or a bromine. It really doesn't matter. So let's go ahead and stick a chlorine in there. This is the benzyl alcohol. And this one as well can go with the SN2 reaction in order to form the ether. So either ones they are okay. It depends now what chemicals are available in Beyond Labs. So we see that we have the benzyl chloride, so we're going to go with the benzyl chloride route. Okay, so we're going to choose the benzyl chloride, and then we don't want any of those solvents. We don't want a polar solvent. Remember, this is a Williamson synthesis. It is an SN2 reaction, so we don't need any of those. So we're going to go ahead and put a diethyl ether in there. We don't have methanol because we would need methanol in here. So if I'm looking, yeah, so we need a methanol in there. We don't have methanol, so that will lead me to see over here that, okay, we have the sodium methoxide. So we have the sodium methoxide. This means that the first step of the Williamson is already done for you. Because to make the sodium methoxide, you need a base to come and take the acidic hydrogen of the methanol to make the sodium methoxide. So that first step is done. So probably this lab is for the second step of the Williamson synthesis. So we're going to choose the sodium methoxide in there. Just let's bring it all the way here. Okay. Go to the live data. Just make sure that the sodium methoxide is there. So I have everything in here. I have the benzyl chloride. I have the sodium methoxide. So now if I'm looking at the mechanism of the reaction, I'm going to skip the first step of the Williamson because we already have the methoxide. So for the mechanism of the reaction, I'm starting with the benzyl chloride. It's a simple SN2 reaction. And I'm having the sodium methoxide. So that is going to be step 2 of the Williamson synthesis. And this is going to be the mechanism again of the reaction. So the nucleophile is going to come, it's going to attack the carbon, and the halogen is going to leave. Guys, there is no way we can have elimination in there because we do not have a beta hydrogen. And this one is a benzylic, it's a simple benzyl chloride, it's a simple primary alkyl halide. So it's a primary alkyl halide, so the reaction is going to be pushed towards the substitution. I would end up getting my product in this case. Okay. plus of course the byproduct, which is the salt that we would need to get rid of when we are doing the purification step of the product. So we have everything in. We're gonna put our condenser. We don't need the heater because, or the heating manitle, because we are not doing elimination. It's a substitution. It goes at room temperature. Do not forget your nitrogen gas. And then please do not forget to take a TLC. That is going to be your reactant. This is a reference. This is your reactant. Get the RF value. Let's save that. Get the RF value, and then we're going to start our reaction. Make sure that you are in the live data. We're going to process we're going to process the time. And as you can see over here, you keep processing the time until all your reactants, which is the benzyl chloride, turns into a product. So now you know that your reaction is complete, and this is going to be your byproduct in there. So now the reaction is complete. We're going to go ahead and do extraction. Why do we want to do extraction? We want to do extraction because we know that sodium chloride is a salt, right? And because it's a salt, we can simply, we have a diethyl ether in there. So we can use the extraction method where we create the two layers, the aqueous layer and the organic, in order to isolate all the impurities in our product. So right now I have everything in there on the screen. Don't add acid and don't add a base because you don't need those. You add an acid and you add a base whenever your byproduct is either acidic or basic. But here, if your byproduct is salt, we can simply use water in order to extract it. So if you use the water in there, you're going to create both layers. The top layer is the organic, and notice, like in your top layer, this is what we need. We only need our benzyl methyl ether, which is our product. So we're just going to take our top layer in there. We're going to put it here. The bottom layer, we don't need it. This is the sodium chloride and the water. We're just going to go ahead and dispose of it. So this is going to be our product in there, and then we're going to go ahead and take a TLC for it. Calculate the RF, please, and let's go ahead and save that. We can go ahead and get an IR spectrum. Guys, please read your spectrum from left to right. Since we are working with an ether, we want just the ether stretches. I know I have a benzene, but I don't care about the benzene. This is going to be my functional group in there. This is what you made. So let's stick to the ether stretch. So we do have an ether stretch, which is the CO. We have different types of stretches in there. This is an SP3 CO stretch and another SP3 CO stretch in there. Okay, so we do have the CO stretch, and the CO stretch of the ether. If you take a look at the IR table, this is the SP3 CO stretch. It's between 1025 and 1200. We do have two of those actually. So it's going to be in this region in there. So this is the 1025. This is the CO stretch. And we have another one at 1100 as well, which is another CO stretch. So these are our stretches in there that I want you to report. Of course, you have the sp3ch stretches in there, but this is because you have an sp3 carbon. This is not a functional group, so do not report this. And in this region over here, we do have the C double bond C of the benzene. Again, do not report that. Just focus on this region, which is the ether region. We're going to save the IR spectrum. And then we're going to go ahead and do the proton NMR. So for the proton NMR, see how many signals you have. You have 1, 2, 3, and 4. And again, please read your NMR spectra from the left to the right, meaning from the higher chemical shift to the lower chemical shift. And if you scroll, you can easily write down the chemical shift for every single peak. Now, I know that in this region over here, in the 7 to 8, this is your benzene. So I do have a benzene region in there. These are the different hydrogens of the benzene. And then I do have two singlets in there. And then notice like these are singlets. Notice how narrow it is. Notice the top, how it is sharp in there. Notice the top, how it is sharp. So there is no splitting pattern in this case. Okay, so let's go ahead and zoom in. If you zoom in, we can see that those hydrogens in here, those hydrogens, they are higher in intensity than this signal. So probably this signal over there corresponds to one hydrogen. This one is going to be more than one hydrogen. You can do the integration as we did last time and find out the number of hydrogens that correspond to every peak. What we have is the different types of hydrogens in here. So we do have a hydrogen here, we do have another hydrogen there, we do have a hydrogen over here. So this is going to be hydrogen A, that is going to be hydrogen B, that is going to be hydrogen C. And then definitely hydrogen A is going to be over here, and then hydrogen B is going to be over here. And then we do have another signal that corresponds to hydrogen D. This is going to be hydrogen D. And then the last signal, which is going to be the last signal, which we believe is going to be further upfield over here, that is going to be hydrogen E. Okay. So always, if you look at your NMR spectra, the first signal that you see, this is peak 4. Okay, so the last signal or the first signal that you see, this is going to be your CH3. So the CH3 here appears at 3.38. Let's put our here you go, so that to make it easier. So our first signal in there for the HE, that is going to correspond to a chemical shift of around 3 point, we said that it is a 3.38 parts per million, and that is going to be a singlet. You can easily see, I mean, read the number of hydrogens in there. It needs to be 3 hydrogens. When you do the integration, this needs to have 3 hydrogens in there so that your answers can match. Okay. And then the second signal is going to be the CH2. So this is always the order. You start with a CH3, a CH2, and then a CH. So the CH2 over here is going to be signal number 3. And this one is going to be around 4.34 parts per million. So this one is going to be around 4.34 parts per million. And definitely it's a singlet because there are no hydrogens on the neighboring carbons. So it's going to be a singlet. And the number of hydrogens that correspond to that are 2 hydrogens in there. Again, your answer has to be the same as the integration calculation. And then we have our benzene hydrogens here. The benzene hydrogens, they correspond to signals 1 and 2. So peak 1, peak 2. And again, please read from the left to the right. And whenever you are filling your data, if it tells you peak 1, please write the answer for peak 1 in there. So peak 1 corresponds to, see how many hydrogens in peak 1? So I would say that peak 1 is the most de-shielded compared to peak number 2. So if peak 1 is the most de-shielded in this case, see, I do have 1, 2, 3 signals in there. So 3 different types of hydrogens. So peak 1 and 2 correspond to these 3 different types of hydrogens. Now it's obvious that peak 1 correspond to hydrogen A and hydrogen B. Peak 1 corresponds to hydrogen A and to hydrogen B. So let's put it this way. So peak 1 corresponds to hydrogen A, hydrogen B. Why? Because those 2 positions in there, the hydrogen A and the hydrogen B, these are going to be the most de-shielded because they are closer to the oxygen. So that is going to correspond to peak 1, and peak 1 shows a chemical shift at 7.92 parts per million. And from the integration, you should know or see that this corresponds to, see how many hydrogens? 1, 2, 3, and 4 hydrogens. So it's going to correspond to 4 hydrogens. In most of the cases, the para hydrogen is different than the meta and the ortho hydrogens. So the para hydrogen now is going to be further a little bit upfield, and that HC over here, it's going to correspond to peak 2. So this HC is going to correspond to peak number 2, and that is around 7.37 parts per million, and it's going to correspond to 1 hydrogen. Again, the peak area for peak number 2 has to have a corresponding 4. 1 hydrogen corresponds to peak area number 1. So you can easily see the difference in the intensities over there. Guys, please remember that the region between 7 and 8, this is strictly for the hydrogens of the benzene. So here I can see that my benzene has 4 hydrogens and then another 1 hydrogen from the integration data. So this is going to be a mono-substituted benzene.